Hello, my name is Rogelio and I am the RoboBoat team leader, overviewing several areas inside the project.
Hello, my name is Alex and I worked on the development of the USB guidance navigation and control system.
Hi, my name is Rodolfo Kwan and I'm head of vision and perception of the team. I supervise and develop projects related to this area.
Hello, my name is Ivana and I worked on the model predictive control collision avoidance strategy.
Hello, my name is Jorge Carlos Medina, leader of the embedded systems team in charge of implementing the microcontroller units.
Hello, my name is Sebastian and I worked on the development of the gazebo simulation environment and on the velocity obstacle method tested for collision avoidance.
Hello, my name is Ian.
VantTec began participating in RoboBoat competitions in 2017. Since then, improvements on the boat subsystem have been made year after year to increase the overall performance. Although we have acquired promising results in terms of perception, control, and motion planning over the years, we still lack a reliable collision avoidance method, integration of our two perception components, and a suitable algorithm for the Hydrophones process.
The path-following controller based on adaptive sliding mode control and line-of-sight guidance law, developed for the previous RoboBoat competition, remains in charge of our vehicle's motion control. This system relies on readings of the IMU VN300 for position and velocity feedback data.
Perception in the USB is achieved using two main sensors, the Z stereo camera and the Velodyne LiDAR BLP16 POC, being positioned at the front and at the top of the USB respectively. The current system has two functional object detection methods. The first one is a YOLO Tiny Tree convolutional neural network trained to detect voice and markers using the input image from the Z stereo camera. The second one, which is the improvement of this year, relies solely on the LiDAR to detect the same object but using a 3D point cloud. There's still work required to unify the readings from both methods with the sensor fusion approach.
The obstacle avoidance techniques make use of the available sensors to compute suitable avoidance maneuvers against obstacles in the path of the vehicle. This year, two approaches have been developed to assist the obstacle field and the obstacle channel challenges: the original velocity obstacle implementation and a model predictive control based collision avoidance method, where the latter one achieved a better performance.
The urge to overcome limitations in our microcontroller unit arrived when in our last competition, the Arduino responsible for handling the signal processing of the hydrophones failed. Because of this, a more robust and reliable system was needed. So an STM32 microcontroller unit with more computer capabilities, better sampling precision, and bigger memory banks was acquired.
An array of 3 hydrophones to be placed at the front of the boat was considered for the acoustic docking challenge. This array does its signal processing on the STM32 based on the different frequencies given by each hydrophone. Currently, the signal processing works only on a Python and MATLAB simulation using the music algorithm. This approach consists on computing the angle at which the detected signal is located, but only for a 2 dimensions case, with only 2 hydrophones.
Based on the presented system, the boat should be able to solve almost all of these addition challenges. Developments made during the last years in path-following control and object detection systems have given us the confidence in achieving the mandatory navigation and the speed gate challenges.
Further advancements of the perception system and collision avoidance methods developed during these competitions have also led us to improve our approaches towards the obstacle channel and obstacle field challenges. Due to limitations caused by health concerns, testing has only been done in a simulated environment, which we'll further talk upon in the next developing and testing segment.
In previous years, the Z camera using the Jolly neural network was the main object detection source for the perception system. This system, along with the IMU, proved enough to complete the mandatory navigation and the speed gate challenges solved in previous editions.
The obstacle channel and obstacle field solutions proposed last year were expected to work based on the latest point cloud readings and a modified velocity obstacle method for collision avoidance. The approach worked on some scenarios, but after further tests, This collision avoidance method was discarded as it didn't deliver the expected performance.
The acoustic docking challenge developed last year presented the performance of the algorithm on a simulation, but lacked the integration of the LiDAR and Hydrophones readings.
The efforts for RoboBoat 2021 took focus on the improvement of the perception system and the obstacle avoidance methods. For the mandatory navigation, speed gate, obstacle field, and obstacle channel challenges on research-based approaches and practicality based on simulations.
The perception system received an implementation of a less resource-intensive object detection algorithm using the point cloud from the LiDAR. This system was validated through simulations in the mandatory navigation and speed challenges.
For the obstacle avoidance problem, the velocity obstacle method was implemented, and a new NPC-based collision avoidance method was developed. These methods, along with the improvement on the perception system, were robust enough to complete the obstacle channel and the obstacle field challenges.
The acoustic docking challenge received an improvement in the simulations, as LiDAR readings allowed us to identify some trace of the dock necessary for the correct functioning of our algorithm. And by adding a simulated signal representing what we will get from a hydrophone array, we can determine which is the desired docking bay.
This challenge algorithm works well under the RV simulations. Due to time concerns, it was not yet validated with the LiDAR readings, but will still need improvements as we are not able yet to realistically simulate the hydrophone and pinger, and the signal algorithm is not yet implemented.
Development of the object delivery challenge was halted due to complications caused by the API provided for the drone, redirecting our focus to increase the confidence rating of challenges we could already complete. Our confidence in the mandatory navigation, speed challenge, obstacle field, and obstacle channel is high due to the fact that our sensors can be simulated and also the environment, which is enough to validate the performance of the algorithms.
In the real world, we will have to worry about uncertainties, external disturbances, noise in the sensor readings, and unexpected objects or situations. Verification of the proposed solutions in the real world is still pending as we follow the government's health guidelines.
With the current pandemic, physical testing has been highly difficult due to health regulations established by the state government. This has proven to be a big challenge for testing, but hasn't affected our motivation and willingness to work and develop our projects.
The simulation approach was similar to last year's. RVS was used as the visualization tool for mission algorithms, focused more on the development of the obstacle channel and the obstacle field challenges. But to improve the perception system, the use of gazebo was required, as it allows to simulate vision-based sensors such as the Z camera and the LiDAR. An IMU was not required to be simulated as its data could be obtained by using the mathematical model of the USB.
It is in both gazebo and RVs where we were able to measure the efficiency, viability, and robustness of several iterations of our mission algorithms and system implementations, such as the LiDAR 3D object detection and the collision avoidance methods.
Also, worlds in Gazebo were created, where full models of the challenges and the unmanned surface vehicle could be found to provide our developers an easier and faster way to test their implementations for their designated tasks.
The signal detection algorithm was developed under a MATLAB and Python simulation. It is able to compute an angle corresponding to the location of the pinger, but only in the 2D plane, and not included in the presented challenges solutions. Further improvements are still necessary to obtain an algorithm that works in a 3D space.
Also, the signal processing on the STM32 still needs further development, as physical testing was not possible due to the pandemic.
The simulation results demonstrate the capabilities of the proposed task solutions. Results show the proposed course approach is feasible, as the course tasks involving only the USB were successfully accomplished.